So we are reviewing properties of logs. The reason why it's review is because we do talk about properties of logs in Algebra 2. However, like a lot of things go oopsie doopsie out of our head. Okay. So we're not going to spend as much time as we would in Algebra 2 on the log properties because it's supposed to be a review topic, not a brand new topic. Okay. So up first, we're going to talk about for any positive numbers, m, n, and b, where b cannot equal 1, so your base cannot equal 1, and p, any real number, the following properties apply. So the first up is our product property. Your product property is saying that when you have two arguments being multiplied inside of a log, they can separate into their own logs, and they're added together produces the product. Okay, it ties with our exponential rules, right? When we have two exponents that are being multiplied with the same base, all you're doing is adding their powers, right? Does that make sense? Mm-hmm. Okay. It doesn't matter if it's log or natural log, the rule applies. Okay. Next is our quotient property. If your argument has division taking place, you can separate the argument into subtraction of the numerator and subtraction of the denominator. So you can subtract your numerator, the log of your numerator minus the log of your denominator. And again, it applies also to natural log. Okay. The last but not least is our power property. So with our power property, it's saying that the power of your argument is actually your coefficient of the log. So the power of your argument is going to be the coefficient for your log. Okay. Here also, you can notice that it applies to natural log as well. So these are going to be the three properties that we manipulate and test out for this part of the notes. Cool? Make sure my pen, I don't know, it was working just fine this morning. And now it's like, wiggle, 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 wiggle. There we go. It's working. All right. So up first, hey guys. Up first, we have here, it says to expand. When you're expanding, that means you are separating the argument into as many separate terms as possible, log terms as possible, okay? So up first, we have log of 8 times x times y to the 4, okay? So that means I have how many terms that I can separate? 3. There are 3 factors, so I can create 3 terms. Does that make sense? Okay, so we have log of 8 plus log of x plus log of y to the 4. So the first rule we applied was our product property. I'm going to call it PP. Product property was applied. Okay. There's nothing to be multiplied. It's just how the rule works. It's just the rule. It's up there. Yeah, it's the first one on the list. No, I'm just saying, like, I don't know the value of x and y to multiply anything. It's our product property. All right, so not that right now. So here we go. We are on next. When you are expanding, that also means that there is no powers being present. So the exponent is going to have to change. Now, I can't call this PP2, so I call it EP for exponent property. But it's your exponent property. When I have the exponent property, what that means is that whatever powers I have now become coefficients. So my final expansion would look like, well, not final, log 8 plus log x plus 4 log y. Okay, back in Algebra 2, this is where we would have stopped at. Does that ring a bell? We would have stopped here. However, we're now in pre-calc. We do not stop here, and that's because 8 can be broken down to a power. And because 8 can become a power, that means that I can fully expand it. How can I express 8 in terms of a power? 2 cubed. 8 can be replaced with 2 to the 3rd power. Because 8 can be replaced with 2 to the 3rd power, that means I can now apply the exponent property here. So my final answer would be 3 log 2 plus log x plus 4 log y. And that would be the fully expanded Because 8 equals 2 to the third power. The 2 is the base and 3 is the power. We replace 8 with 2 to the.
Would we just do the same thing as we did like the first time and just do the exponents? Like 3 log. What's that called?
Power property? We just did it?
Like just a regular thing we did to like
Converting?
yeah.
Oh, no, you're not converting.
No, but to make the exponential.
If I was converting between exponentials and logs, but I'm not converting between exponentials and logs right now. Yeah, we're just expanding. That's what it says right here. We are expanding our logs. Yes.
Could you combine those together to create
You can't.
log of x?
If I combine, I come back to where I started. Yeah, we expand it. So if I was to condense, I go back to that. You undo what you did.
That's 2 times 2.
2 to the third equals 8.
And we have log of 8.
Like, okay, that's what I'm asking. Are we doing the 2?
And I said no. Like, we're not converting between logs and exponentials. We're not converting. You're just, what can I substitute 8 in that has a power? I can substitute it with 2 to the third. Like if I saw 4, I'm like, oh, that's 2 squared.
3 log 2.
Yeah, because the exponent goes to the beginning.
Okay.
Yes.
Like once you.
Yeah, that's the rule. It's not what we were doing last week. Those are 2 separate things. That's what I'm trying to tell you. That's the property that we just went over while y'all were talking. That's this property. So it's saying your power becomes your coefficient.
Okay.
All right. So on to the next. So on this one, it's natural log, still applies, but now I'm dividing. Because I am dividing, that lets me know that I'm using the what property? The quotient. I'm going to be using the quotient property. So the first thing here, though, before I apply the quotient property, is this square root needs to be written as a power. How can I write the square root of something as a power? It's a fractional exponent, does it?
1 over the x squared.
There we go. So it's going to be x squared plus 5 to the 1/2 over x. So now I'm going to apply the quotient. The quotient rule is telling me that my numerator, the log of my numerator minus the log of my denominator. So the log.
We make that square root into a
The-
into an exponent. Because like a square root is the same as to the
A half power. If I'm taking the root of something, I'm taking the,
out of the or out
Yeah.
of the-
so we have natural log of your numerator. My numerator is x squared plus 5 to the 1/2 minus the natural log of my denominator, which is x. Next, I'm going to apply the exponent or power property here, right? So that's going to move my half to the front. My exponent becomes a coefficient. So we have 1/2 natural log of x squared plus 5 minus the natural log of x. No more properties can be applied. So then this is my final answer. EP, power property or exponential. So the power property or exponential. Okay, so that is when you are expanding. Condensing is saying I want to combine these 2 logs or 3 logs into one single log. Okay, so yes. Division. The argument.
And then there was an exponent.
Yes. All right. So here, we have natural log of x to the 5 minus 2 natural log xy. You're going to go backwards. So the first thing you want to ask yourself, are there any exponent power properties that I can adjust? That one's good, right? but it's okay to just put it together because I'm trying to
Yeah.
condense. So then this is going to become the natural log of x to the 5 minus the natural log of xy squared. So I'm going the other way. All right, I am subtracting. So I'm dividing. It's the quotient property, right? So now I'm going to apply the quotient property. The quotient property says that the first term that's being subtracted is my numerator. The second term is my denominator. So it's going to be the natural log of x to the 5th divided by x to the y squared. Okay, I can simplify. That's the difference here. You want to make sure you fully simplify. I have x to the 5th in the numerator and x squared in the denominator. Can I simplify that? When you're simplifying, what are you doing with powers? You're subtracting. What is 5 minus 2? So it's x to the 3rd in the numerator and y squared left by itself in the denominator. You want to make sure you simplify
So it takes out x, but it leaves the y squared.
because the y had no one to be eliminated. Okay. At this point, making an assumption that you understand that this can go to the numerator and to the x and to the y. So this is saying x squared and y squared. Do we understand that? When it says condense, your job is to make it an exponent, make it one. Yes, that's why I tried to write it so you can see that we're going to do the EP first and then decide. Okay.
When we use EP, are we still going from left to right, or are we like trying, is it already gonna be in this format? Are we going back?
I don't know what you mean left to right.
Like, you know, whenever we're doing like. It's like this format.
If you're going backwards, then you're putting it back as a power.
So it's already gonna be this format.
I don't want to say yes because I don't know what that format. What do you mean by this format? When you're using power, it's saying I'm going from here, I'm taking the coefficient and making it a power. That's going the other way. This one's saying I'm taking the power and make it a coefficient. It just depends on which one you're doing. So if I'm expanding, I'm going to make it into a coefficient. If I'm condensing, I'm going to make it into a power. All right, so again, we're going to start off here. Are there any powers that I can condense? I can use both for EP. So I'm going to apply this. It goes to the entire argument. Does that make sense? This goes to the entire argument. So I'm going to have the natural log of x to the 9. It's you multiply. Y to the 3rd. The power property of exponents is that you multiply when there's parentheses. And then plus the 2 is going to the y and to the z. So natural log of y squared and z to the 4.
Do we always start with exponential when it's condensing?
Yes.
And then what do we start when you're expanding?
Either your product or quotient, depending on which one it's at. So what is this going to be?
Or why?
We're going to multiply. Why am I multiplying? Plus, so we're going to be using the product property. So it becomes the natural log of x to the 9th, y to the 3rd, times y squared, z to the 4th. I'm going to simplify. Okay. Does x have a friend? Nope. Does y have a friend? So it becomes y to the 5th Does Z have a friend? No. So my condensed form is,
Wait, but Miss Jones,
yes.
whenever you say we're multiplying like x9 and y3 times y squared and z to the. Why wouldn't you multiply them? Like, technically, it is like right? Like, why wouldn't you multiply the powers 3 and 2?
This is the product property of exponents. When you're multiplying two exponents with the same base, you're adding their power.
Why did we do that?
Okay, let's write it out. So if I have 2 squared, oh fudge. It's two different operations taking place. If I have 2 squared to the second, right? That means I have 2 squared times 2. Oh, twos are a horrible thing to do it with.
Oh, like the number.
You're
also,
multiplying the
not
whole thing. But
So
2
that's
is
why
a
we
horrible
do
thing to do it with. I don't know where you mean earlier. Here?
In the red?
In the red?
It's just because there was parentheses. Like, why did we make it a 9 instead of?
Because I'm just, that 3 would have been here. And I'm distributing that 3. 3 times 3.
But if it's just like, where there's no parentheses, like.
Yeah. So the reason being is here, when I have 2 to the third square, that means I have 2 to the third times 2 to the third, right?
Oh.
And that equals 2 to the 6. You add them together, right? But if I have 2 to the third times 2 to the second, these are just numbers. These are not being multiplied. So that means you're adding these two together. I have 5 2s that are being added, multiplied together. So this is 2 to the 5th. Those are two different operations taking place. This is your power of exponents. This is your product of exponent. Power, product. Okay. Powers are distributed. And product is added. Okay. Do we see the difference between the two operations? All right, cool. All right, so next up is our change of base formula. Change of base formula is a little bit of a unnecessary thing for the most part. The reason why I say this is because unless it's just asking you to approximate, to give the exact value, it's going to be, it's useful in that sense when you're trying to find the exact value. But if it's on a calculator section where you're allowed to find it in the calculator, then you can press buttons in the calculator to find the approximate value of any log base. Remember, this is the first go for all of us. We shall see. All right, but so I'm just going to make a note of if you're using your 84. So if we're using the TI 84, there are two ways to get to change of base. Way number one is by pressing the math button and then arrowing up twice. And when you arrow up, you will see log base. So 84, option number one, is you press math up, and then you'll see log base. Okay. In 84, you also can access it by pressing alpha window 5. So the other option in the calculator is alpha window 5. And it also will give you your log base.
I think
It's in the, it's a different, well, that's why we learned change of base. So whether you're using updated 84 or not, change of base is going to work regardless. Okay. How change of base works is that you are, if it's a base A, you're going to take log B. You're going to take the log of whatever your base is. And it's not supposed to be an A. This got weird. It could be anything. You can make base of anything. It could be a base of 5, base of 10, base of whatever you want it to be, as long as your argument, the log of the argument is in the numerator, and the log of the base is in the denominator. Same thing here. If you have base of 10, so if I have base of 10, it's going to be, again, log of the argument in the numerator, log of the base in the denominator. Natural log, a lot of times it's usually reserved for, you don't really need to use this because it's going to work either way. It's just weird. It's just an extra thing. Either if you do any of these, it's going to all result in the same thing. And we're going to show you in the calculator. Okay. So change of the base. It also allows for you to do logs from your phone. So if you're just trying to find a quick log, you can use your phone because this is something you can easily type in your phone. And I'm going to model it with a regular calculator as well. So I have log base 3 of 13. So log base 3 of 13 can be rewritten in 2 ways to put into any calculator that has scientific mode. Way number 1 is I can do log 13 over log 3. We learned it last year. You know why I know you learned it last year? Because we're doing it right now in Algebra 2. Or natural log of 13 over natural log of 3. Either one of these will produce the result. Okay, so let's go to our basic calculator. So if I just go to a regular computer calculator, see, I'm just clicking on a regular computer calculator. I'm going to make sure it's in scientific mode. And now I'm going to take the log of 13 divided by the log of 3. So we have the log 13 divided by, what did my calculator do? Or not. It didn't want me to be great in that moment. Let's try that again. Divided by log of 3. Hit enter. And it'll give me my answer. 2.3347. Okay. On the hand, if it's a calculator section of the test, on your handy dandy TI. Mm-hmm.
So if it works with, like, what is the difference between natural log and log? It's like if they're each other.
It's just to make sure you understood. If you're on a very old 84, you have to go to the catalog to get to the catalog. It's second 0. So that's the oldest way of getting there. Fastest way is going to be alpha. Where's L? L. Alpha. Take me to L. And you'll see, and you'll be in the L's. You can scroll all the way down if you want, but it's all the way in there if you're on an older calculator, which is annoying to worry about when you could just use change of base, right? Because that's what I did in school. We just used change of base. There was no point of going all the way to second catalog and scrolling all the way down. Under catalog?
Yeah.
Then it's just older than that.
Log logistic.
Then you have no choice but to do change of base. Yeah. And it's not that big of a deal. So change base, log 13 divided by log 3. You are using, you can change the base. It doesn't matter. As long as the base of the numerator and the base of the denominator are the same, your answer is going to be the same, no matter what. That's why natural log of 13 divided by natural log of 3. What do you notice? It's the same. If I did alpha window 5 and I type in 3 and 13, what do you notice? It's the same, okay? I repeat again, it doesn't matter. If I go to math, arrow up to log base. Again, however you get there, however you type it, the value is going to be the same. So I would like you to take 60 seconds or less and do the last 2. Four decimals. Practice writing your change of base, especially if you have an older calculator. All right, are you ready to tell me what we got? What did we get for B? What did we get for C? Because that means 2 to the negative 1 power is 1/2, and which we should have known that. Approximate, because I rounded. Oh, I didn't mean for negative 1.
So I was like,
You saw nothing. All right, yes, good. All right, now we're going to talk about things and how this is useful when you are evaluating transformations of a function. So when graphing log functions in the form of y equals log base b k times x, we can show that the product property y equals log b of k plus log b of x is equivalent to a vertical translation of the parent function, okay? So a horizontal dilation is the same thing as a vertical translation for a log function. You hear me? That's because of the product property. I can rewrite it as a vertical translation, okay? So that's what we're gonna do. So we have up first, log base 2 4x. Well, I can rewrite g of x using the product property, right? Instead of 4x, it becomes its own. It equals log base 2 of 4 plus log base 2 of x. Okay, so this is my transformation. Does that make sense? This becomes my vertical transformation, whether I'm going left or right, because log base 2 of 4 is just a number. So 2 to what power equals 4? 2. So log base 2 of 4 equals what? 2. So I have 2 plus log base 2 of x. So all this is telling me is that I'm taking my parent function, log base 2 of x, and I'm translating it up 2. Does that make sense? Okay, so now we're going to graph both. So we're going to graph our parent function, which is f of x equals log base 2 of x. So in order to graph that, remember that logs have vertical asymptotes at x equals 0. And when I'm plotting my points, it has a x-intercept at 0, 1. At 1, 0, I'm sorry. And then for 2, it's going to be 2, 1, 4, 2, and 8, 3. I didn't put random numbers.
no, I know.
Oh.
Are you putting X like 1, 2, 4? To be like log X two?
The log base 2 of 1 is 1. The log base 2 of 2
No,
is, oh, I plugged it in for x. 2 to what power is 2? 2 to what power is 4? 2 to what power is 8?
G of X, like in those numbers to do.
We're not going to plug in anything. We just have to shift it up 2. So to find our g of x, because we found that it's just a transformation, all we're doing is shifting it up 2. Uh-oh, sorry. Guys, we're going to finish. If it lets me change my pen color, it won't let me change my pen. Oh, there we go. All right. So I know that for g of x, it is a vertical shift up. 2. Huh? Oh, yes. Sorry. But here we're going, so I'm going to go, instead of being at 1, 0, we're now at 1, 2. Instead of being at 2, 1, we're at Instead of being at 4.2, we're now at, instead of being at 8.3, we're now at 8.5. So now we are doing this. So instead of us having to manipulate the x's, we just had to count and move our y's. Okay, how do we feel? Doable? Okay, so as our x increases by 1 unit, the y values were shifted up by 2 units. Yes? Okay,
Hey, is that purple vertical shift like up? The answer is
yes, yes, yes.